Hello, I'm Zhong Denkei from South China University of Technology. I'm excited to present our work, CorrCLIP, a training-free method for open vocabulary semantic segmentation. The goal of OVS is assigning a semantic label to every pixel in an image based on text descriptions. It can identify and segment objects from a virtually unlimited range of classes. To achieve this, the vision language models emerge as a natural starting point. Trained on massive web-scale data, CLIP has demonstrated remarkable capabilities for open vocabulary classification. To leverage this for OVS, a critical adaptation is to shift its learned correspondence from the image text level to a more granular patch text level. However, CLIP's contrastive image text training objective leads the patch representations within Vision Transformer to be dominated by global features rather than containing distinct, localized semantic information, which is important in segmentation tasks. As shown in the figure, CLIP's attention maps are very noisy.
Previous methods have attempted to mitigate the aforementioned limitation by modifying the self-attention mechanism in the final layer of the Vision Transformer. Some methods modify the attention mechanism to compute self-attention based on query-query or key-key similarity, instead of the conventional query-key.product. This encourages each patch to focus more on itself, thereby improving the attention maps to some extent.
Some methods calculate attention scores using Vision Foundation Models features, which are more coherent. This further improves the attention maps. However, previous methods don't explicitly identify the specific patch correlations that are detrimental to segmentation. To investigate it, we divide patch correlations into two types, intra-class and interclass correlations. We first restrict the scope of patch correlations to intra-class. It notably improves CLIP's segmentation performance as shown in the figure, demonstrating that intra-class correlations benefit CLIP's segmentation. We then gradually introduce interclass correlations. Performance declines as the interclass correlations increases. Even interactions with the most similar interclass patches lead to performance degradation. Here we use DINO to measure the similarity, which are known to be more semantically coherent. Additionally, intra-object correlations are sufficient to enhance CLIP's segmentation capability. This further demonstrates that interclass correlations are the main reason for the limited segmentation performance of CLIP.
Based on these findings, we reconstruct patch correlations in CLIP to suppress detrimental interclass correlations. We tackle this with a two-stage method. The first stage is scope reconstruction. Its purpose is to strictly limit where patches can interact. To do this, we leverage a powerful class-agnostic mask generator like the Segment Anything model. It provides a set of object-level masks for the image. By forcing attention to only happen within each mask, we create hard boundaries that effectively prevent most interclass correlations. We also merge highly similar masks to better approximate class-level regions. However, these generated masks are not always perfect. An object mask can sometimes contain other objects. Here comes our second component, value reconstruction. Value reconstruction aims to reduce the correlations inside these imperfect masks. We use features from DINO to calculate similarities, which downweighs the influence of the remaining interclass correlations. And our experiments shows combining DINO's query and key embeddings works better than output features.
As shown in the figure, the scope of patch interaction is restricted to within the same class. With the correlation reconstruction, CorrCLIP effectively reduces interclass correlations and improves segmentation performance. Beyond fixing the correlations, we introduce two additional branches, Semantic and Spatial branch. For Semantic branch, we repeat class tokens at the start of Vision Transformer, each corresponding to one mask. In the attention layers, each mask class token only attends to the image tokens within its corresponding mask to capture mask-specific semantics. At the end of Vision Transformer, each image token is summed with its corresponding mask class token to enrich the semantic information. For Spatial Branch, we incorporate lower layers features into the final patch features to enhance spatial details.
Besides, CLIP lacks spatial consistency due to its weak supervision. Although our correlation reconstruction alleviates this issue, it still falls short of the performance achieved with full supervision. So we introduce map correction. Improve spatial consistency by setting all patches in a mask to the mask's most common category. This further improves spatial continuity and edge detail. As shown in the figure, each module delivers a solid performance gain and scope reconstruction providing the largest one.
We evaluate our method against SOTA methods on 8 standard segmentation benchmarks. Our CorrCLIP greatly outperforms existing training-free methods. Here, we visually compare CorrCLIP with Trident, a leading prior method that also leverages the SAM and Dino base models. As shown, CorrCLIP correctly recognizes the object class. To further assess CorrCLIP's open vocabulary performance, we tested on several out-of-distribution datasets. These datasets are distinct from the general classes in standard benchmarks, such as person, dog, road, car, chair. We used 4 datasets covering diverse foods, various birds, water bodies, and underwater scenes. On these datasets, CorrCLIP beats the fully supervised methods trained on the COCO dataset, which is similar to standard benchmarks. This proves our CorrCLIP can generalize better by truly using CLIP's open vocabulary power. CorrCLIP showcases its open vocabulary power by segmenting images across diverse domains, for example, movies, anime, a vast range of categories, for example, various fruits, animals, and even fine-grained subcategories, for example, different dog breeds, cats by color. Besides, because CorrCLIP is a training-free method, it can seamlessly inherit the advanced capabilities of its underlying model. For instance, when we build CorrCLIP on top of MetaCLIP World, it naturally becomes a powerful multilingual segmentation model. We test it in 4 different languages. Its segmentation quality stays consistently high. Finally, let's make a summary. First, we identified that interclass correlations are a bottleneck for CLIP segmentation, so we use scope and value reconstruction to suppress them. We further boost performance with feature refinement and map correction. CorrCLIP performs well across many benchmarks. That's all for my presentation. Thank you.